In today's lecture, we want to finish with the theoretical concept of radial migration according Professor Triller. And then I want to introduce an alternative model of equidistant migration to you. Last time we obtained the equation zeta is plus minus 2 pi by d squared times r, 2p by d squared times r squared, so that it is an equation of paraboloid on which is lying Triller's idealized fiber. So, based on this equation, we can make a small rearranging, so that first say that we start from point r0 zeta 0, then the c must be equal 0, and this ratio 2p by d square explain in this for r square by d by 2, and this is divided by 2. Yeah, it is divided, and this divided denominator it means multiply, so that it's well. Here use this r square by d by 2 square as a quantity capital Y. R square by d by square, what is it? R by d by 2, what is it? It's a relative position of fiber point between 0 and ion surface. On the ion axis, this quantity is 0. On the ion surface, this quantity is 1, isn't it? Yeah, but it is square. This is in square, so y is square of this ratio. So defined here is y. Then our equation is possible to write in the form zeta is pi by 2 times capital Y. Yeah, because this is capital Y. Why is this here? Then this equation is a linear equation between zeta and quantity y, capital Y. And here I'll use the traditional, I can say statistical quantities. For example, he said that interesting can be so-called fiber mean position. What is it? It's mean value of his quantity capital Y. It's called under the term fiber mean position. When we use equations derived for Triller's ideal model, we can easy to obtain that fiber mean position here is 1/2, 1 by 2. On the place of y, y is here with zeta is this one, isn't it? You, and we can the responsible result we can obtain on the lengths from 0 to pi by 2, 1/2 of period, because there it is periodically same. Well, fiber mean position for Triller's model is 1/2. The second quantity which recommend here for calculation in the ion is so-called RMS deviation, standard deviation. What is it? It's a standard deviation of quantity y. The definition is this here. Okay, using this, after rearranging which is shown here, we obtain from Triller's ideal model 1 by 2 times square root of 3, so that it is 0.2829. Yo? And the third characteristic of Hirel, it is the intensity of migration. It is dy by d zeta square times d zeta, integral of them, by d zeta. Yo? So, and square root then from this one. So, because this is linear, it is slightly something like linear. Linear is the relation between zeta and the Hirel's quantity y. Yeah, it is linear. So fiber path in this diagram is this red. Linear from 0 to one periphery and then back and so on. Yeah, and such angle, this angle, this is the sense of the intensity of migration, or better say the tangents of this angle. Well, so there are three quantities which are very often used in the works which study the internal structure of different yarns. A lot of authors don't think about these quantities, only take it as a final equations from work of Hirel and applied it on some experimental research which they are doing. It is in literature little also generalized, not only to the Thrillers model, also exists some term in literature like the incomplete migration, which is not where the fiber is not going from 0 to yarn periphery, then is in some distance of radiuses only, and so on and so on. More than you can obtain these relations. All this you can in more details to read. For example, in the very known book of Hirel and co-workers, Structural Mechanics of Fibrous Yarns and Fabrics. This book is very known. Professor Ishtiaq or Dr. Das, can you show it? Okay. Let's compare the result of Thriller with an experimental experiences. This is the fundamental equation. From this fundamental equation, square root of this one, and multiply both sides by tangents beta, and we obtain such equation. It's relation between some function of beta on the right hand side and tangents alpha times tangents beta on the left hand side. When we calculate this, we obtain the curves, the thick black lines. This is absolute value of tangents alpha times tangents beta, dearest tangents beta, or 2 pi rz. We obtain the thick lines by when we take an approximated equation, when we use an approximated equation, so we obtain this equation, so that the absolute value of tangents alpha tangents beta is constant. Such constant is the dotted line here to this here. The dotted line is an approximation of original function of Thriller's model. If k is high, you can see here that in most part it is roughly very good. Well, and how is now our experimental experiences? We measured three-dimensional curves of fibers inside of the yarn. How? Principially only. We used so-called Morton's tracer fiber technique. When you use the good immerse liquid to yarn or to each textile object, then all fibers stay be transparent, like from glass. When you produce yarn having small value of black fibers which was before process colored to black, then in immerse liquid you see transparent yarn, and the projection of black fiber, projection of black fiber. You see it. Other fibers don't disturb in immersion liquid. And when you have two projections of same fiber, perpendicular projection, one time from this light, one time from this light to this yarn. When you have it, then from the known relations from descriptive geometry, you can reconstruct three-dimensional curve of fiber, isn't it? Principally, it is clear. So we reconstruct a lot of parts, three-dimensional part of fibers in the yarn. Then we obtained in each radius or glass interval of radii, we obtained the corresponding angles, the mean angle alpha, mean angle beta, mean angle gamma, and so on. Yeah, and we were through this way using calculator, using computer, we was able to evaluate this relation experimentally too. The experimental curve based on different yarns, it was a relatively large set of yarns. This work was produced with mentioned Dr. Mahin Kumar Soni. These curves have the trends as shown in the green area, like this or this or this area. So a set of curves each for another yarn. So the trend of such curve is quite other than the trend which we obtain from Taylor's ideal migration model. We have totally different trend. What we need to say, Taylor's model is not valid. Sorry, but it is so. In the time of Taylor creation of this theoretical model, it wasn't enough experimental possibilities to experimentally verify this model. This is first point. Second time, that Taylor's model was very good from other side for other scientists, which can use a lot of ideas, a lot of imaginations, which started Professor Taylor. This work stay be, from this point of view, useful to these days. Well, because this model wasn't good, was not correspond with the yarn, we said we need to start another model. Model which we call model of equidistant migration. In Taylor's model, we introduced number new of elements intersecting the cylinder with radius r on one fiber per unit length of yarn. Generally, it is a function of radius r, but the model of ideal migration assumed constant value of nu based on the idea of representative fiber intersecting all radii. This idea is not well imaginable, not well imaginable, because since the differential layer near an axis, for example this blue layer, has a very small volume, so that very small surface, hence the number of fiber intersections can be also very small there. Is one point. B, since the differential layer near yarn surface, the green one here, has already small packing density, and the number of fiber intersections will be also small there. On the yarn periphery, the packing density is every time smaller in reality, so that the fibers can't the chance to be here so often than in the middle radii, isn't it? Therefore, maximum number of intersections is in the red layer between blue and green. Is it imaginable? Okay. So, it's evident that the model path of fiber can be regular but random. Can't to go every time from axis to periphery, then back to axis, then back to periphery, and so on. Regular can be only directions, means derivatives of elemental increment. So that then the created model is not pure deterministic as earlier. The diagram here R zeta illustrate the given idea. On the place of assumption for nu, yes, nevertheless on the for our model we use on the place of earlier assumption for, what was earlier assumption for? Earlier assumption for say that nu is constant. Number, what is nu? What is nu? Sense of nu? Number of intersections in given radii in yarn lengths and per one fiber. Yeah? We say no, it is not constant, it needn't be constant. This number of elements is proportional to the fiber volume into the vicinity around radius r. When in the vicinity around radius r is a lot of fiber material, then probably a lot of intersections will be there. When no, that only a few intersections will be through our radius r, isn't it? This is our modification of assumption. And other version than the assumption used by Triller. How is fiber volume in the differential layer at the radius r? So, 2 pi r dr, absolute value because it must be positive for calculation of volumes and so on. 2 pi r dr is a total area per one differential annulus, our known differential annulus. Okay. Times yarn length, delta zeta, it's volume of our differential annulus. So that this is volume of our differential annulus times packing density, it's volume of fibers in our differential annulus, isn't it? Yo? After small rearranging, this volume of fibers in our differential annulus, we can write, it's only graphical rearranging. R is changed with R, evidently, and mu can be changed 2. We needn't to think about the constant value of mu. So they are changed. All other members in this expression are stable, are constant. So this expression in brackets, it is some elemental, differentially small, constant, same for each differential layer, isn't it? And this value say volume of fibers in differential layer on the radius r. So we can say this is constant, variably are r and mu. Yeah? So we can say that our nu must be proportional to the quantity r times mu. Yeah? Because we said, yeah, higher is volume of fibers in vicinity around the radius r, so higher is the number of intersections, blah, blah, blah. Well, so this equation must be right in our model, where C is some constant of proportionality. Number of intersecting points on one fiber per unit length of yarn related to the cylinder with radius r, and it is nu r. Just 2 intersecting points must be on the length of period of migration, outside, inside, from center of the yarn to periphery and back. Then the number of periods on the fiber per unit length of yarn is 1/2 of nu. Because I think it must be evident, yeah? Number of intersections per one fiber and 2 intersections, the lengths corresponding to 2 intersections represent the period lengths. So this equation is valid, so that the period is 1 by nu r by 2. Because nu by 2 is number of periods per length unit. Yes, so we can derive the period of migration now. After rearranging, we obtain this here, we obtain, and using small c as a constant, which is 2 by constant capital C, we obtain that the period P is C by R mu. Then also nu R is 2 by P, so it is 2R mu by C. Okay. And how is now the fundamental equation for our equidistant migration? Before the using assumption 4, we derived such equation. So it is valid also now. On the place of nu, we use this expression. So this here, we obtain this, we multiply and divide by 2 pi, and it must be equal to this. It's only rearranging of this equation based on a new which have a new definition, so that we obtain this here for tangent square alpha. This is constant. Inside of brackets it's a constant. This constant I want to call Q, capital Q. So we can write the tangent alpha square is 1 plus tangent square beta, by q square minus 1, where q is given by this, I have this structure, the constant q have this structure. This equation is a fundamental equation of our equidistant migration. Well, on the page 61, it was derived that n times s is this, and this too. The derivation is there. We can use this relation. Then also q, which is pi c by ns. Using this on the place of ns, we obtain this here. So q is c by d by 2 times u times 1 minus c. It's some constant which related to our earlier constant of proportionality. Then 1/2 of yarn diameter, packing density, and 1 minus delta. Yeah? Our couple of differential equations for equidistant migration is following. First is trivial, it's same as for helical model, same for Taylor's model, stable. Second is interesting. Now from fundamental equation, square root of this is here. Tangent alpha is dr by d zeta, tangent beta is 2 pi r z, so that dr by d zeta is plus minus square root of this quantity. This is differential equation between increment of radius and increment of zeta. Yeah? This equation is possible to solve analytically. It is not elliptical integral. So after integration, we obtain this equation. Plus minus r is r2 parts, from inside to outside, from outside to inside every time. Now, I think we need not to comment it step by step. We must to do this integral. All is constant. All is constant, but r is integrating variable. Yeah? It is possible, how you will see here, include the substitution which is here, so you can quietly home to study how to integrate it. Resulting integral value is here. Yeah? The second is trivial, so integral from d zeta is zeta, it's evident. Well, and using this, we obtain this here, where some k in the moment is the integrating constant. So, the relation between r and zeta is given by such equation in equidistant migration model. Graphically, it is shown on our picture. Sorry, the yellow color is too light. These are the set of directions which are valid. So that our fiber must follow the trends which are in this yellow net. Yeah, it is relation between r and zeta. You can see it is not linear. There are some curves. It was really calculated by program. It is not linear. It's not linear lines. It's some curves. But practically, you can see that these curves are very near to the the straight lines. We will then make something with them. Why I call this model as an equidistant model? We know that cosinus theta r is dr by dl and is given by this expression. By using the fundamental equation in this expression, we get dr by dl is this one. Evidently, this is the same. Tangent square beta plus 1 is also in our fundamental equation. Where it is? Here it is, yeah? So it is q square minus 1 times tangent square alpha. Where I use it here, so I obtain this here. Tangent square alpha is going before square root, so that says here. And what is this here? Tangent alpha by absolute value. Plus or minus? Or plus 1 or minus 1? Plus, minus. So we obtain dr by dl is plus minus 1 by this, but this is constant. So it is plus minus, if q is, it is shown high, it's a constant. Yeah, if q is very high, or oh, sorry. Yeah, just a moment. It is this one. In some approximation, we can say it. We can obtain. Obtain it in a given expression. So here, the fiber length increases. Fiber length dl. This is important. Fiber length increases equidistantly with steps of radius. Increasing of radius, the increment of radius is increasing of length is proportional. Fiber length is proportional to increasing of radius. Yo. Therefore, equidistantly. Increase equidistantly with step of radius. Therefore, this model is called as equidistant migration. So its interpretation, why the term equidistant? Also in this model is possible to construct some approximation. You saw that our curve was very similar to the straight lines. So let's assume, as earlier as by Taylor's model, the tangent square is much more smaller. Tangent square beta is much more smaller than 1. Then tangent square alpha is, this is very small value. So that 1 plus something very small is roughly 1. This is 1, and so that it's 1 q square minus 1. So it is constant. It's constant, and we can, tangent square is constant, square alpha, so that tangent alpha is constant 2 plus minus. So the dr is constant times the zeta, or the zeta is constant times dr, how you want. And then we obtain that zeta is some constant, square root of q square minus 1, times r. It's linear function. It's a linear function. Plus k based on starting point. If the starting point is in the point 0, 0, then k is 0, 2. It's integrating constant. Which of equation it is? A linear relation between radius and axial coordinate zeta. What it have? Cons. So there are, it is equation which characterize cone. In this model, the idealized fiber is lying on a cone surfaces. You? Well, and this picture can show, can help how to imagine our fiber. At first, fiber is not going every time from center to periphery, from periphery to center. It is going maybe from center to some radius, then back. The point is not on the periphery, it's in a radius, then back to smaller radii, then back to higher radii, and so on and so on. Yeah? So that the trajectory of the fiber can be like this red curve. in the diagram r zeta, of course. Yeah. Well, you can imagine it as here. The fiber is is on the surface of some cone, then break its curve and go to smaller radii or to another cone, then break it and go back to on the surface of the third cone, and so on and so on, like this here. So is the picture of fiber trajectory, which is random from point of view of points in which break and change the direction from inside to outside or from outside to inside. And we obtained such a result. Now the comparison with experiment. We change only one assumption called number 4. On the place of idea of constant nu, which represents that each fiber must go from periphery to center and from center to periphery, we assume that the quantity of intersections of radius is proportional to the vicinity of fibrous material around this radius. We measured it experimentally, how I explained when I discussed the results by Trilor. And they are the same diagram. Here is tangent beta, it means 2 pi rz, and here is the absolute value of alpha times tangent beta. Our curves in equidistant model are the thick curves here, and the approximation which we used, they are the dotted lines here. And the same trend of experimental curves. It is this, and the experimental curve was so or so or so and so on. Yeah? Of course, it's not ideal, but I think it's much more better correspondent the theoretical model with experimental experiences. And we only change, only one idea is changed from assumption 4 to newer assumption 4 star was called it. And experimental graphs from you can see this is a mean value of cosinus, absolute value of angle theta r on different radii inside of yarn from 0 to yarn surface. Here is radius, abscissa have the scale of radius from yarn center from 0 to 1 is because here is r by d by 2. Yeah? Cosinus theta experimentally measured is this here, like this. Two examples are here, rotor yarn and carded ring yarn. Both from viscose fibers. We analyzed viscose yarns because viscose fibers was the best for experimental work based on the transparency of such fibers in immersed liquid using Morton's tracer fiber technique. You can see that roughly the values can follow our ideal model. This value is constant, equidistant migration. You? Here no, but this is the sphere of Hyrenis outside of yarn radius. Period of migration, pure experimental results. Also ring yarn and rotor yarn. Length of mean period of migration, and also r by d by 2. You can see that period of migration is not constant based on radius. As we assumed, it is higher value in the region around yarn axis, because small surface of cylinder in small radius. Therefore, no too often the fiber have the chance to go inside and then outside. Therefore, number of intersections is small. Therefore, the mean length of period is relatively high. The same is on the yarn surface. It is increasing because packing density on the border between yarn body and hyaline is small. Therefore, fiber is here only sometimes. Yeah? Therefore, the period is higher, and the minimum period, so maximum of frequency of intersection, is in this central part, as we assumed. Some notes to the source of migration. The people, the colleagues of Professor Hirl, studied the migration in filament yarn. They take filament yarn having a small twist from production. You know that we often give small twist to filament yarn because be enough compact for manipulation technological process, isn't it? Yeah. Well, and this filament yarn, they twist it, and then on a twisting machine, and then they studied the migration, and he obtained some migration, some period. It was very periodical effect. Why it is shown here? From couple of cylinders, last couple of cylinders, the filament yarn is going out flat as a ribbon, and then the twisting follow the mechanisms of ribbon twisting. What is it? I have here a microphone, I must speak carefully, but I prove it. This is a ribbon, my tie. When I twist it so, this is the character of ribbon twisting. And the fiber which is on this side, then in this side, yeah, for example, my yellow strips on my tie. Now the yellow strip is here, but also inside, outside as well as inside. Therefore, they obtained periodical migration, which is bring-in migration from the character of starting product, twisted, a little twisted filament yarn. In more details, it is in the book of Hirl and coworkers. The second mechanism of bring-in migration is random bring-in migration. When you will see the thin sliver, very small sliver, which is going out from last couple of cylinders in a ring spin machine, you can see that not all fibers are perfectly parallel. They have some distribution of directions, isn't it? And this distribution is going inside to the yarn structure. Therefore, we can see the change of radius as well as the change of local twist to fiber element. So that the migration, the second influence is a random orientation of fibers in the ribbon which is coming to creation of the yarn. This is maybe the most frequent mechanism of migration. Morton, this name was here mentioned with tracer fiber technique, was also a professor on UMIST in Manchester, older than Trillor and Hirl. And he mentioned that exists some mechanism which is known as a mechanism of fiber length compensation. When we twist yarn. The fibers, the peripheral fibers, have some force, axial force. They was elongated. Therefore, they want on this red fiber exists some axial force. So that's why fiber want to go in, because the resulting force is this one, isn't it? Do you imagine it? If it is possible, this fiber wants to have this trajectory as this straight line. And the fiber which are inside of the yarn have the length enough, because it's a little compressed, it can go outside. Therefore the fibers can change mutually. This is the principle of Morton's idea. But based on my personal meaning, this effect is not too high. Why? It exists very significant friction between fibers. And change the fibers need very high forces because the friction don't want to do it. Yeah? Therefore, based on my personal meaning, I think that this mechanism is not too important. Then exists the third mechanism. When you will see, when you will watch what is doing, and in a spinning triangle, you will not see only the fibers which are going immediately to the to this top point of triangle, to the yarn. You will see its scheme, but you will see something like here is in this triangle, some twisting of the yarn together. This mechanism, then the structure, because friction and so on, is partly coming to the yarn, so that the fiber is change radius, because the starting structure can be this one. Also, this is a mechanism for a fiber migration, and a lot of others. About some of them we spoke in my book, but sorry for you, it is in Czech language. Good for you is that the Czech language is possible to read. Your professor, Professor Ishtiak, he knows speak Czech. Well, this is all for today. This theme was a little more theoretical, but I hope these models, or through these models, minimum you can better imagine how is the structure of a real yarn, and then you can imagine what you need to do in a process of spinning, in a spinning process. I think also different modifications of spinning technologies try to make a better structure of starting, maybe a ribbon of starting product, this small sliver, because to obtain the yarn with no too intensive migration. This is more. It has the chance to have higher value of packing density, be more compact, and so on. Yeah? But it will be a question of our next lesson. Packing density, compactness, diameter, and so on.